Now again, I stored the code from before in a separate package with a separate file in a subfolder, and now I got an empty main.go file again. Because now I want to dive into a new concept called recursion. What's that? We talk about recursion if a function calls itself. And a great example for this is a function that calculates the factorial of a number. Just to make sure we're on the same page, the factorial of 5 would be 5 times 4 times 3 times 2 times 1. So it would simply be 120, because 5 times 4 is 20, times 3 is 60, times 2 is 120, and times 1 is, of course, still 120. And if we want to derive this, we can write a function for this. The factorial function, for example, which takes a number as an input and returns a number. So it's a standard named function, nothing special about it yet. Now, to derive the factorial here, we could write this all with help of a loop. So without any new feature at all. We could add a result helper variable, which is 1 initially, and then write a for loop where we have I as a helper variable, which starts at a value of 1 though, not 0, but 1, where we keep on looping as long as I is smaller or equal than number, and where we increment I after every iteration. And then in the loop, we can set result equal to result times I. So in the first loop iteration, this will be 1 times 1, which of course is 1. In the next iteration, it will be 1 times 2. Thereafter, it will be 2 times 3, and so on. And in the end, we can return result here. And now in main, we can use this function to get the factorial of a number, let's say of 5, by calling factorial with a value of 5 for the parameter. And then we can, of course, use the format package, as we always did, to output this factorial. If we save all of that, and we then run this module, I get 120 here. And for 6, for example, if we save this, I would get 720. For 3, on the other hand, I would get 6. So this works. And this is not using anything new. Now, there is nothing wrong with this approach, but with recursion, we can write this in a slightly more concise way, and in other cases, recursion can have even bigger advantages and solve problems which can be difficult to solve otherwise. But here I'll just comment out this loop-based solution and instead show you the recursion approach. Because the idea of recursion, as I mentioned, is that a function calls itself, which is allowed and possible in Go. So here inside of factorial, I can execute factorial, so that same function in which I am. Now I can do this to multiply the number which I get as an input with the result of calling that same function with number minus 1. Because in the end, that is what a factorial is. We execute 5 with 5 minus 1. And then we execute the result of this with 4 minus 1, so with 3. And then we execute the result of that with 3 minus 1, so with 2. That's what a factorial does in the end. We deduct 1 from the number step by step, and then execute the result of the previous calculation with that reduced number. And that's what we can do here as well when we multiply number with factorial for number minus 1. And now I'll return the result of that calculation here in factorial. Now we'll look into how this executes in just a second, but there is one thing that we have to define in addition to this return statement. Something you have to define in every recursive function. You have to define an exit condition, otherwise this is an infinite loop. Because you keep on calling yourselves, and you just lower the number, at some point we'll go into the negative space, but we'll continue calling ourselves. And hence we would have an infinite loop, and that would crash our application. Hence, you always need an if statement that allows you to exit out with a different return value where you don't call yourself. And here I want to check if number is equal to 0, because I don't want to multiply with a negative value, and I also don't want to multiply with 0, because if I would multiply with 0, the overall result would be 0. And therefore, in case of number reaching 0, I will return 1 instead as a hard-coded value. And with that, that's the recursive implementation of this loop. Not much shorter, but a bit shorter, and as I mentioned, recursion can also solve different problems, and hence it is important to understand its concept. Now, before we dive into how this executes, to fully understand how it works, let's see whether it works. And therefore I'll save everything, and then just execute this all again, by again running this module. And for 3, I get 6 as I did before. For 5, if I enter 5 here, I instead get 120. So it does work. But how does it work? Well, this line here, line 6, executes first. And we pass in 5 as a value, so 5 is received here. This if check then executes, and 5 is of course not equal to 0, hence this line won't execute. Instead we make it to this line. And here we then multiply 5, because that was our input value, with the result of calling this same function again with 5 minus 1, so with 4. So before we then overall return here and yield the final result, this function here executes. Because if you call yourself inside of a function, before the main function executes, any inner function calls have to finish. And that's the case no matter if you call yourselves or another function. A function can't finish its execution and can't return a value before it has gotten back values from any other functions it might have called inside. And that's the case for calling itself as well. So here we are calling ourselves with 4, 5 minus 1, and hence this function executes again, a second time. And that's important. We now have 2 executions of the same function with different values. And the execution that was started first, with a value of 5, is simply paused until the second execution finished, with a number of 4. So now this function executes again with 4 as a value. It's still not equal to 0, so we skip that if check. And now we reach this line in that second function execution. There, number is 4, so we multiply 4 with, again calling ourselves, this time with 3, 4 minus 1. So now we have 2 ongoing function executions, and we're starting a third one. The other 2 executions are paused. That third execution receives 3 as a value, so again it's not 0, and we start another new execution where we multiply 3 times factorial for 2, 3 minus 1. So now in that case we again execute this, the number now is 2, it's still not 0, hence here we now have 2 times 1. Because number minus 1, if number is 2, yields 1. So again, we have another ongoing execution of factorial with number equal to 1, still not 0, so we execute this line again with 1 times factorial 1 minus 1, which is 0. So again, that function starts. We have a couple of other function executions in the hold right now, but a new function execution starts now with 0 as a value. Now we make it into this if check, so now we don't reach this line, and we return 1 instead. So now we have the first function execution that did really finish, and that 1 is returned to the function execution that we started before, where number was 1. So now we have 1 times 1, because that was the return value for calling this function with 0. And therefore we return 1 and another function execution finished. Now we return that 1 to the function execution that started with a number of 2 before. Here we now have 2 times 1, and finally we can return 2 here, and another function execution stopped. Now we return that to the function execution of this function where we had 3 as a number. We have 3 times 2, that execution stops and returns its value 6 to the function execution that was started before with a value of 4. So now we have 4 times 6, which is 24 of course. That function execution stops, and now we come back to that original first function execution that we started a while ago. Here we have 5 times 24, which was the result from before, and that's 120, and now that's returned. Now all the factorial executions finished, and now we got that result here. That's how this executes behind the scenes. And it's very useful for problems like this, but also for other problems, more advanced programming problems, where recursion can often be a neat and convenient way of solving a certain problem that might be hard or even impossible to solve otherwise.